We are recording. Yes, thank you for reminding me. Okay, so chapter 6, we're counting. Chapter 6, I'll be doing sections 1 to 4. Two obvious quick motivations like that. The first one is finite probability. It's based on counting. So everything, if you ever do any kind of probability, which might happen, all of this will be very useful. And the other obvious place where counting is of importance is when you're trying to evaluate the time and space requirements. If you're doing a bit of theory, if you are, so if you're evaluating an algorithm, how much time or space that it's actually taking, so you'll have to do some counting, obviously. I'm saying obviously, but maybe it's not obvious, but trust me. Okay, so we're going to start by some very, very elementary, very elementary counting principles, which, yes, they will be obvious. The principles themselves are obvious. It's how you use them, is how you apply them, which is not always so obvious. So basic counting principles. Now, I don't really like the way that they're presented in the book, so I'm going to be presenting them in a slightly different way, but that's my personal choice. Okay, but let it be said that accounting basic accounting principles are based on bijections. Yeah. So that's what counting is. It's just basically, yes, thank you. Thank you for your encouragement. It is. Okay, so all based on bijections. Right? So you remember what a bijection is. You have a map between two sets, which tells you basically they have the same number of elements. And so if you're counting one set and you have a bijection to another set, then you know that they have the same number of elements. So you can infer things like that, right? So bijections again. So this is what's a bijection? We have a function f from a set A to a set B, which is 1 to 1 and on to. And so the cardinality of A has to be equal to the cardinality of B. Okay, so let's start with the most obvious of all basic counting principles, which is the following. I will call this the sum rule because that's how it's called in the book. But what the sum rule says is very, very silly. It says that if you have two sets, A and B, and all the sets in this section are finite. We're just counting finite stuff. So if A and B are disjoint, if these two sets have a empty intersection and you count the number of elements in their union, that is the same as counting the elements in A and counting the elements in B and adding them up. So I think everybody is okay with that, right? So that's what I would call the sum rule. That's all it is. Okay, so in other words, if you're going to count something, you can cut it up into pieces, count the different pieces and add everything up. Okay, so that's a very general, simple principle, right? More generally, we have the following version, is that if you have more than two sets, you can still do the same as long as they're all disjoint, right? So if, let's say, AI and AJ are disjoint, right? So if two sets AI and AJ are disjoint, you have a whole bunch of sets A1 to AN, then the cardinality of the union, I mean, this might look, hopefully this looks okay. If you're having trouble with the notation here, I can, okay, I'll rewrite it after just in case. So the cardinality of the union of these sets, they have no elements in common at all, then this is the same as adding the cardinalities of all these sets separately, right? So in other words, so if you count the union, I'll just rewrite it like that. This is the same as just adding the cardinalities of all the different parts, right? So they're all disjoint. So, okay, so this is the general version. So for two sets or n sets, it's the same thing, okay? All right. Now, I think in the book, they start with the product rule, but I wanted to sort of spend like 30 seconds more on the product rule, and I needed the sum rule to discuss it. So let's move on to the product rule, and then I'll do a bunch of examples. So let's move to that. Here we go. Yeah, the product rule. I'll give you the. Again, these are not formulated in the same way in the book. They're formulated in a sort of semi-informal way, and which proves to be great if you understand everything. And if you don't quite understand everything, then it's sort of meh. So I'm adding these more formal versions, which might help you. Okay. And if you don't need the formal version, you just look at the informal version and everybody's happy. Okay. So what is the product rule? It says that if you want to count the number of elements in the product of two sets, it is the product of the cardinalities. That's the product rule. Okay. Now, I'd like to discuss this just a little bit more. So if you remember what A times B is, so A times B is the set of all pairs AB, where little a comes from big A and little b comes from big B, right? So these are all the pairs in that order. Okay. So how do I make sure that, I mean, if this is obvious to you, that's great, that's fine, okay? And if it's not, then let's just see how we can count these elements, these pairs, right? So what I can do is split it up. Okay, I'll just illustrate. Okay, so here's a little example. Let's say that I take A to be 1, 2, 3, and B to be XY. Okay, so then A times B is the set of all pairs where the first entry comes from A, it's either 1, 2, or 3, and the second entry comes from B, it's either X or Y. So I'm going to list them in a specific way, which is the following. So this is all the pairs that start with 1, and then all the pairs that start with 2, and all the pairs that start with 3, right? Okay, so I've listed them all, and you see that in fact, so notice just to, so you can use the sum rule. Okay, so I'm not doing a formal argument for the product rule in general, but it comes from the sum rule, basically because you see this is the set of all pairs that start with 1, union the set of pairs that start with 2, union the set of pairs that start with 3, right? And hopefully it is clear that each one of these sets has the same number of elements as B, right? And there are how many of these cardinality of A? So notice, so there are cardinality of A disjoint sets, each of size cardinality of B. Okay, so I just illustrated in this little example, but you can see that it's the same thing in general, so that the product rule comes from the sum rule, basically by splitting up the set in the nice way. Okay, but of course, if you believed that this was the case, that's fine. That's great. Okay, let's do some examples. Some easy, some not so easy. Okay, here's our first example, which is, I think, easy. We're asked to count. So how many license plates can be made if each plate contains a sequence of 3 uppercase English letters followed by 3 digits. Okay. Now, I'm doing this a little bit more formally because in my experience, whether as a student learning this stuff or as someone trying to show it to other people, is that sometimes things look like, yeah, okay, I know how to do it. Here we go. I do it. And then you look at the answer and you go, no, I didn't get it. And you're not quite sure why. Okay. In counting problems like that, you have to be careful. So, so that's why I'm sort of giving you little very formal tools that you can always fall back on when things don't work out. So here's the situation. I have license plates that look like this, right? There are clearly 6 symbols. These are letters, and these are digits, right? Now, yeah, I didn't give you the general product rule, which I should have just before this example. Sorry. I'll do it now. Sorry. Damn. But before, sorry. Product rule, general form. Damn. I hate doing that, but it happens. Okay. So the sum rule for 2, that was like the sum. The product rule for 2 was the product. And so when you generalize to n sets, you can guess what this is that the cardinality of a product of n different sets, this is the product of the cardinalities of these sets, right? I forgot to give this. Exercise, you can try to prove this using induction, starting from the case 2. So if you want to try that. The case with 2 sets. Right? So you can try that. Or if you believe it, then you're fine. That's okay. That's great. Okay. So I'm going to use this version, obviously, to solve my problem. So let's go back here. Let's copy this. Sorry about that, man. Oh, well. Okay. So you can see that what you're looking at are exactly 6 tuples where the first entry comes from the set of letters, the second entry also, the third entry also, and then the next 3 come from the set of digits. So we have a bijection. We're counting. So we are counting the tuples in the set A times A times A times D times D times D, where A, bad choice, but anyway, so crap. So A is the set of letters. I should have called it, I'm going to change that. Let's call it script A. Okay. And D is the set of digits, right? Okay, so that's what I'm counting. And the product rule tells me that the total number will be simply, you just take the product of the cardinality of these sets. Clearly, this set has 26 letters. If you didn't know, now you know. And the digits, there are 10 of them, right? And so the total by the product rule is 26 times 26 times 26 times 10 times 10 times 10. And if you're interested, this is actually not that much, 17,576,000. Okay, so that's the total number of license plates that can be produced with these with this pattern. Okay. Now, once you know what you're counting, it's easy, right? I mean, just the application, the problem is to make sure that you know exactly what you're counting. There's some extra difficulties that will creep up eventually. And I can tell you very, very simple looking counting problems can be very, very tricky. Here's a first difficulty that will, it's a common difficulty, which is you're asked to avoid certain repetitions. Okay, so so avoiding repetitions, very common. Okay, so here's an example. So how many, and we'll get back to that several times during the lecture. So how many elements of the set A squared, or A times A, do not, let's write it properly, have the form A1, A2, where A1 is different from A2. Okay, and I'm going to use this example. I mean, you see, it's like a sort of theoretical looking example, and I'm going to use it to illustrate a useful counting trick. So here is these, well, actually two different counting tricks. Here's a solution. So we know that the total number of pairs in A squared is cardinality of A squared, right? So if I count by the product rule tells me I have, but now I'm counting some stuff that I don't want to count, okay? But we do not want to count which ones? Those pairs which have the same entry, to count the pairs AA with A and A, right? These guys, we don't want to count them. How many are there of these pairs with the same coordinate? Hopefully you see this.
There would be magnitude of A.
Mm-hmm. So there's exactly one for each element of A. So there are cardinality of A of these, right? So it means that what I'm counting, so here, the first trick, and I'm going to illustrate this trick in just a sec in more detail, but I'm trying to count something with a certain restriction. So what I do is I count without restriction, and then I count those which are the bad ones, and I subtract, right? So the total I'm looking for, so total without a repetition is size of A squared. That's counting all of them, but then I'll remove those that I don't want to count. So that's the total number, okay? Now, there's a completely different way of seeing this, which you can see. I mean, if you look at this, size of A squared minus size of A, this can be rewritten as follows, right? I can factor out size of A. This is size of A times size of A minus 1, which actually shows you another way of seeing this. Okay, so this illustrates a different approach, which can be very, very useful. Okay, as follows. Okay, so I want to build pairs that come from A times A, but in a way that the two entries are distinct. Okay, so we build or count pairs A1, A2 with A1 different from A2 as follows. So for the first entry, how many possibilities do I have? I can choose anything I want, right? So there are size of A possibilities, right? Now, once I've chosen that, the second entry, I can choose whatever I want except the one that I chose for the first entry. So there are size of A minus 1 possibilities left. So all except the first entry. Okay. And that's another way of interpreting this number. So you have A possibilities for the first entry times A minus 1 possibilities for the second one. Okay, that's another one, another way of seeing it. Now, if right now you see this and you think, yeah, okay, I can see it, I understand it, perfect. If you don't quite see it, that's great. Also, because it is not so obvious why this should actually count everything the right way. You have to see this as a tree, and I don't want to go there, but that's okay. So to make sure this is a good count, you can see it from my previous count, which was perfect, which was great, no problem, okay, and the subtraction. But this interpretation is saying, okay, I choose here and then I choose what remains and I multiply. So why does this work? You have to look at this from a tree diagram, but I don't want to go there. But if someone really needs me to explain it, I will, but I'll do it individually. Okay, I won't do it. Okay. All right. So let's see if I can do another one like this, which is similar. Yeah. So here's another example. Typical problem like this. So a company, this is the part I really dislike, is just writing down the questions is so long. A company with 2 employees, Alice and Bob, them again, rents a floor with 12 offices. Each employee gets his or her own office if each employee gets his or own office. How many possible configurations are there? Okay, So in other words, how many ways are there for Alice and Bob to choose their offices, right? Different offices combinations. So this is easily seen by the previous principle as follows. So you say, okay, Alice has a choice of 12 different offices. So Alice has a choice of 12 offices. Once Alice has her office, Bob now has 11 choices. So the total number of possible assignments of offices to Alice and Bob is 12 times 11. I hope this is okay, that you can visualize this. Is that okay? Yeah?
Yeah.
All right. Okay. I've talked about this. Okay, so let's move on to some counting problems which are a bit more involved. Some more involved problems. So here's one, which is not so bad, but it involves all sorts of little things. Okay. We have a password requirement. It has to be 6 to 8 characters long. What's a character? It is an uppercase letter or a digit. Okay. And the password has to contain at least one digit. Question: how many different passwords are there? Or possible? Okay, so the passwords have 6 to 8 characters long. What's a character? It's an uppercase letter or a digit, but the password must contain at least one digit. Okay, so if you start thinking about this, I would say that the first thing that will come to mind is to count those of length 6 and then count those of length 7 and then count those of length 8 separately and add by the sum rule. Okay, I think this is the first thing that you would probably try. Okay, so first observation, use the sum rule to count passwords of length 6, 7, 8 separately, right? This is, I mean, the sum rule here is a bit fancy. I mean, it's a fancy name for just saying, well, I'm going to count those with 6, with those with 7, those with 8. I'm going to add them up, right? So there are no duplicates. They're all obviously distinct, disjoint sets, so I'm fine. Okay. Now, the second observation, and this is a bit more subtle, and if you try to count these, so let's start with the 6. Okay, so let's consider 6 characters. So I have 6 characters. Each one of them is either a letter or a digit. That's great. And there's no restrictions on repetitions, which is great. That's always good news. But I have to make sure that there is at least one digit. Okay, so could you just add a blank character to the 7th and 8th characters when counting? I'm not sure. Not sure what you mean here. Sorry, Jacob. I see. Yeah,
Well,
yeah.
instead of counting the 6,
Yeah.
7,
Okay.
and 8
Yeah.
separately, you could count them all together, but just put a blank character instead to indicate there's nothing there.
Yes and no. You're going to run into trouble because yeah, so the blank character, it's not, I mean, you could, let's say we just count I'm not sure. My feeling is that this is going to be way too complicated, but and you're going to have to make special cases because I okay, you say, let's say, well, let's just count. Not my intuition, it's not, is this is not going to work. It's not going to work well, but I see the idea that you have, but I think this is going to be very complicated if you try it like that.
Okay.
But I'd have to write it, you know, I'd have to just really focus and write it down, which for some reason I can't right now and I don't want to do.
Yeah, that's fine. That's fine.
Okay. Okay, so let's just see if what happens if I'm trying to count all those that I want which have at least one digit. So now you might argue and say, okay, maybe that digit is in the first place and then I'm going to count those, and maybe it's in the second place, and maybe, but then you say, okay, but wait, I could have two digits, right? So there could be one in the first, and then it's a huge mess. Okay, so if you try to count this directly, it's going to be messy, and I think this is what is going to happen if you're trying with those blank characters. Going to be something similar, although again, I haven't parsed it totally, but trying to count directly will be very tricky. Okay, so what do you do? Look at the negation of that condition. What's the negation of that condition? Is that there is no digit, but then that becomes very easy to count, right? So notice passwords with no digit are easy to count. Okay, so let's do that. Okay, so basically what I'm going to do is I'm going to do like that example earlier where I said I'm going to count everything with no restrictions and then subtract those that don't satisfy the requirement. Okay, so we count all passwords with no restriction and subtract those bad guys. Okay, so let's see. So I've got 6 possibilities, and each is either a letter or a digit. So that's right. So letter or digit, that's 36 different characters, right, in each position. So the total, using the product rule, so the total will be 36 times 36. I'm going to write it like that, but you see it's 36 power 6. Okay, so that's the total number of passwords using letters and digits or digits with no restrictions on the number of digits. Okay, now if you then count those without digits, you can see that it's the same idea, but now you just don't allow digits, so it's only letters, so it's going to be 26 power 6. Okay, now you count those without digits, so it's letters only. That'll be 26 power 6. And so it means that if you subtract, you get those that have at least one digit, right? So at least one digit will be 36 power 6 minus 26 power 6. So that's for 6 characters. 6 characters. How does it work for 7? Well, if you see how this goes for 6, you see how it goes for any number, right? Okay, so for 7 characters, same idea. Same idea. So it'll be 36 power 7 minus 26 power 7. And for 8 characters, same idea. It'll be 36 power 8 minus 26 power 8. So grand total of passwords will be the sum of all these. So 36 power 6 minus 26 power 6 plus 36 power 7 minus 26 power 7 plus 36 power 8 minus 26 power 8. There you go. I hope you see how this goes. Okay. I guess that maybe you have to try it by yourselves to see how bad it goes if you try to do it by counting directly those with at least one digit. I mean, it's possible. You're going to get an expression for it, but it's just very, very messy and long and painful. And it's easy to make a mistake by counting the same thing twice or forgetting to count something. So this is probably the fastest way to do it. Okay. Questions at this point? Okay. Next principle is, we're not going to go into it into detail, but there is a general version of it which is very cool. And it is the principle of inclusion exclusion, and I'm just going to do it for 2 sets, which is, I mean, it's not a big deal for 2 sets, but if you do it for more sets, it becomes very interesting. So this is the principle of exclusion. So it's a very fancy name for just the two set version. Principle of exclusion, inclusion exclusion. I wrote it backwards. Oh well. It's the other way around, but I mean, who cares? Principle of exclusion, the other way around. There you go. Okay, 2 sets only. We don't have time to go into more sets than that, but you can do it. There is a version for any number of sets, but the version with n sets, the formula gets very, very heavy, obviously. But here it is. If you have 2 sets, A and B, and you count the number of elements in the union, it is the number of elements in A plus the number of elements in B. If I leave it like that, it looks like the sum rule, but the sum rule had an extra hypothesis, which is that the two sets were disjoint. Here they might not be, so this is the general version, so I have to subtract the cardinality of the intersection. Okay, here is the proof of this. So I have two sets, A and B. Okay, and I want to count the number of elements in A union B. So I start by counting A. Okay, so I add up how many elements there are in A. And then I count B. Like that. Sorry. Let's make it logical. Okay, so I've counted the elements in A, I've counted the elements in B, but obviously I might have made a mistake because if you look at those in the intersection, I've counted those twice, okay? But we counted A intersect B twice, but we counted exactly twice, right? Every element in A intersect B has been counted precisely twice. And so if I subtract one of those times, I will get the exact count. So that's the argument. Does everybody see why this works?
Yep.
Yeah.
Yep.
Okay, so that's, I mean, you see the inclusion exclusion. So you include everybody and then you exclude some because you counted them twice. If you look at the formula for three sets, it's basically, it's the same thing, but you have to go one step extra because you count, let's say you have sets A, B, C, you count A, B, and C, okay? Now you've counted those in A and B twice, those in A and C twice, and those in B and C twice, so you remove those. But now those in A and B and C have been removed every time they've been counted, so you have to add them back in. So you have a second level going, then including again. If you have four sets, you have more levels, and you can see that you're going plus minus like that. So it gets quite messy. So we'll stick to that version here, the baby version, which is very, very simple. So here's an application of this, which is cute. Here's an example. How many bit strings of length 8 either start with 1 or end with 0, 0. Okay. So let's try to see how this is a job for the principle of inclusion exclusion. So there's an or, right? So you're counting a union. And so there's a good chance that counting both sets and then removing what's in common is a good strategy. Okay, so let A be the set of all 8-bit strings that start with 1, and let B be the 8-bit strings that end with 0, 0. Okay, so what do we want to count? We want cardinality of A union B. That's exactly what we want. Okay. And so this is cardinality of A plus cardinality of B minus the cardinality of A intersect B. The advantage is you see that counting A, counting B, and counting A intersect B are straightforward. So that solves the problem. Okay, so let's see. A, all strings, bit strings of length 8 that start with 1. So let's take a look at that. So I've got 8 bits. And the first bit is 1. So what is the size of this set? Hopefully you see.
2 to the 7?
Correct, 2 power 7, right? That's straightforward. So it's the product rule. Each, it's a tuple of length. Since there's a 1 in the first position, I don't need to worry about it. Each one of these is 0 or 1. So it's just the product rule, right? Okay, good. What about B? B is 8 bits. The last 2 are 0. So this is basically what am I counting? Bit strings of length 6. So that's 2 power 6. Right? And what about A intersect B? So these are the bit strings of length 8 that start with 1 and end with 0, 0. So again, this is straightforward product rule. That's 2 power 5, right? There are 5 free spots. And so what we are counting is 2 power 7 plus 2 power 6 minus 2 power 5. The actual number is, it's 160, but it's not relevant. Okay. Hopefully this makes sense. And obviously I'm giving you these basic principles, which are not like super deep, and I'm showing you fairly straightforward applications of these principles. Obviously, the difficulty is when you just pick a problem in the book, and now you have to analyze the problem to say, okay, I need to use this, maybe not that. Obviously, this is where you practice helps. Okay, here is one last example for this section, and then I'll move on to 6.2. So, okay. So this example is a bit more theoretical, a bit more involved, and it'll be very useful for us. So the kind of reasoning that goes on will be very useful for us in the future, near future. So I have 2 sets. A has m elements and B has n elements. First question, how many functions are there from A to B? Second question is, how many one-to-one functions are there from A to B? Okay. The second question is a bit trickier than the first one. Okay, so let's start with the first one. So I'm looking for functions from A to B. Okay. Now, if you try to see these as, so if you remember how we define functions, these are relations of a special kind. Did I do that in this course? I think I did. Yes.
Yes, you did at the beginning.
If you try to see them like that, it's not going to help. Okay, so what you want to see is something like this. So suppose that A is A1, A2, right up to AM. And you want a function from A to B. Okay, so what does this function do? For each element of A, it selects an element of B, right? But it can choose whatever it wants. There are no restrictions on what the value of the function is at A1. So any value from B will be fine. For A2, any value from B. For A3, same, right up to AM. If you see it this way, it should be fairly clear that a function, so I'll write clearly, a function from A to B is, so this the number of, or is the same as an M tuple of entries with entries in B. Right, so it is something of this form, B1, B2, right up to Bm, with each one of these in B, right? So the first entry is the value of the function at A1. The second entry is the value of the function, so where, I'll write this, where Bi is f of AI. Okay, so what I'm counting are the possible M tuples of entries from B. Now this is just a product rule directly. So this is just the product rule, right? So this, I'm trying to count the cardinality of B to the M, which is B times E times V, right? So this is B to the M, nice notation, which is as given N to the M. Okay, so if you look at all possible, oh, by the way, suppose that you have to do a problem like this and you're not 100% sure, you can always look at small examples to try to figure out, you know, I could do this here, for example, with a small set A, a small set B, and just start to list functions from A to B and say, okay, I see the pattern, you know, to every element of A, I can choose any value from B. I can do this for all, blah, blah, blah. Okay, it can help to figure out what the general principle is. Okay, so the total number of functions from A to B is n to the power m. Okay, now the second question is a bit trickier. That should be clear that it's trickier. So let's rewrite this. This is m, this is n. I want to find the number of one-to-one functions from A to B. So what is a one-to-one function, right? So this will help. If you don't remember what that is, then it's difficult to answer the question. F is one-to-one if f of A1 is never equal to f of A2 when A1 and A2 are different. So it can't map two, it cannot map two different elements of A to the same element of B. Okay, so this is not, I like this picture. This is in A, this is in B. This is forbidden, right? You're not allowed to do that. Okay, so now think of the way we built our function in the previous question. We said, okay, for A1, I can choose any element from B. For A2, I can choose any element from B, and so on and so forth. But now this is not going to work, because once I've chosen the value for A1, I can't use it ever again. I have to throw it away. Okay, but that's a good way of seeing this problem. But you have to be careful, because there is a requirement here. So look at this little picture I just drew. If A has two elements and B has only one element, are you going to find any one-to-one functions from A to B? That doesn't look possible, right? So notice first okay, that if m is greater than n, then there are no such functions. Right? So if the set you're starting with, you're trying to map it in a one-to-one way to the other set, if it has too many elements, you're going to have to crush two elements to the same thing at some point. There is no choice, right? So if m is strictly bigger than n, the answer, the number is 0. That number is 0. Okay, so if m is bigger than n, then the number of one-to-one functions from A to B is 0. That's the first observation. Okay, so now we will assume that m is at most n. Okay, and I'm going to count them this way. And this is what I said about this. If you remember when we counted pairs from A that had no repetitions, I said, okay, for the first one, I have A possibilities. And then for the next one, I have A minus 1. This is this principle that I'm going to illustrate here, but repeated. Okay, so value of f at A1, there are B choices, which is n, right? Okay. Now, the value of f at A2, I can't use that first value that I used, so now I have n minus 1 choices. So I move on to the next one. Now I'm not allowed to use any of those two first values that I used, so it's n minus 2 choices left. And I keep on going until I reach AM. Let's write that properly so that we can actually AM. So now how many choices are left? I've used n for A1. I've used n minus 1 for A2, n minus 2 for A3. So that will leave n minus m plus 1 choices. Now, if you're wondering how I could find that so fast, is because I've looked at it before, obviously, but also look at the pattern. Here, this is n minus 0, index 1, n minus 1, index 2, n minus 2, index 3. So it's always n minus 1 less than the index. That's the pattern, right? So this is n minus m minus 1 or n minus m plus 1, right? Okay, so it means that the total number of such functions of one-to-one function is the product of these. So it is n times n minus 1 times n minus 2, right up to n minus m plus 1. Now, this is a very annoying formula because its length depends on the values, and that's not fun. But there is a way to rewrite that, which is very, very convenient, which is the following. So this is an inconvenient expression. We rewrite it as follows. Okay, so notice that I have n times n minus 1, right? And this is in each term, we're decreasing by 1. So if that makes you think of a factorial, that's great, right? But it stops at n minus m plus 1. So what I'm going to do is I'm going to fill the rest of the missing factorial. So all the numbers So now I'm going to decrease by 1 again. So n minus m. And then n minus m minus 1. I'll just go right down to 1. But wait, I've changed everything, but I'll just divide by the same thing. Right? This is the same as this. Everybody is okay with that?
Yep.
Now, what's the point? The point now is that if you look at the top part, it's actually just n factorial. And what I added, if you look at the bottom, that's n minus m factorial, which is pretty cool, right? This is very compact. Right, so n factorial divided by n minus m factorial, that is precisely the number of one-to-one functions from a set with n elements to a set with m elements, as long as m to n, m less or equal to n. Okay, so I wanted to illustrate a few things in this example. Counting functions, and with restrictions, this principle where if you're not allowed to repeat values that you've chosen, then you remove them. You can still use the product rule in this context. And then there's also this factorial thing that will come back soon, because it's a very useful little expression here. Any questions, comments, anything before I, you know what, it's 13:06. Yeah, no, I'm not gonna start, I'm gonna stop here. Because otherwise I'm just gonna, because otherwise, I don't know, whatever. Okay, I'm just gonna stop here. That's it. Yes. Questions, comments? No. Okay. Oops. Sorry. Wrong button.